Next up, we have Dr. Patrick M. Pilarski. Dr. Patrick is a CFAR Artificial Intelligence Chair, as well as an Associate Professor at the Department of Medicine at the University of Alberta and a Vice Board Chair at AMI. Dr. Pilarski's research interests include reinforcement learning and decision-making, artificial intelligence, real-time machine learning, human-machine interaction, intelligence amplification, rehabilitation technology, assistive robotics, and a longer list. Up next, please welcome Dr. Pilarski.
Awesome. Well, I'm going to get caught on this. I am a chronic wanderer. I like to wander everywhere with my microphone, and I'm going to cause trouble, I know. Hi, folks. Thank you for having me. Hopefully those online can also hear. It looks like, I don't know, I can't see anyone's faces there, so I guess not. I'm going to do a quick, I'm going to jump right into talking a little about AI for bionic limbs. Before I do, though, I like to do a little bit of a straw poll so I know who I'm talking to. How many folks here are from the humanities? Cool. Okay, awesome. Tech folks or science folks? Okay, medicine? Economics? Okay, cool. I could keep going, but I think I've got a good cross section. Who did I miss? Arts? Okay, cool. Other forms of arts. Any faculty colleagues here to like heckle your other faculty colleagues and just give me a hard time? No? Awesome. All right, good. Well, I'm going to keep going then. So I am going to talk to you today about AI in bionic limbs. And in particular, I'm going to give you one specific, essentially a value pitch for artificial limbs that in fact keep learning while people use them. I'm going to focus our discussion today around this particular application of AI or realm of AI within the domain of artificial limbs. Who's familiar with like neuroprostheses, bionic limbs, robot arms that people wear? Show of hands, other than my own graduates. Okay, cool. Good stuff. All right, so a lot of you probably don't know much about artificial limbs then. Is that fair to say? Okay, awesome. So I will still make a statement that I think we probably all will agree on, which is that, okay, a prosthetic limb is often a mechanical or electromechanical system, which is worn by a person to help them live their daily life following usually illness, injury, or accident that has led to them losing their limb. So when I talk about prostheses or prosthetic control, I'm talking about that setting. And really here, the statement I hope that we agree on is that like prosthetic control, the feedback from a device to a person, the actual interventions we choose, and the way we train people to use these devices can be improved by adapting these approaches and sculpting them to individuals, their unique bodies and their unique needs. So this is essentially saying, gee, shouldn't medicine be adapted to the person who needs it? Shouldn't our assistive technologies actually be sculpted to the person who will be using it in their daily life? So, okay, see nod. So like Victoria's nodding. Okay, good. So like you buy this argument at least. One statement that might then be controversial, or that like if I gave this to a room full of medical practitioners or MDs, they might disagree with this statement, is that these same prosthetic devices should continually adapt and sculpt the way they interact with people during their post-clinical deployed use. When someone's at home with a robotic limb, it should be improving over time then as well, not just while they're in the clinic having it tuned. Okay, cool. So to walk through this, I want to paint a little bit of picture where we're at in terms of how prosthetic limbs do actually adapt to people and vice versa. So for this, I'm going to use that little meeple. You can see there's a little, for those online, I'm pointing up at the little gray person. That's the person. There's a little cube. That's the device. And I'm using this particular convention to say, well, you know what? The device is now being adapted to that person. And so in conventional prosthetics, where someone might go into a clinic and just have a hook and cable system that's fitted to their body, they go into the clinic, the box is adapted to them, the device is adapted to them in their daily life, and then they spend the rest of time, often a very long period of time, adapting to this device that's now part of their daily life. So recently we've seen the deployment of things like machine learning and in the control of prostheses. So people could, in fact, actually adapt the devices at home in intervals. And so what we see then is a person might train their artificial limb and then spend a large period of time adapting to it. The limb performance starts to degrade, and then they may train that limb system once again. There's been a shift in industry. I'll just say this is a very recent shift, and I don't think a surprising one, to say that, oh, well, in fact, we might wish to be adapting those limb systems, not just to the person, but to general trends from larger populations of users around the world. Big data comes to prostheses at last, only a few decades too late. And so what I'm going to say is that, in fact, and the whole topic of the rest of my talk to you tonight is, in fact, to say that there's another path, which is that the person and the machine continually co-adapt to each other at the same time for the duration of their interaction. And for some of you may have read, there's a document that Mike Bowling, Rich Sutton, and I put out called the Alberta Plan for AI Research that we shared last year. And one of the commitments in that plan to AI research is, in fact, to what we call temporal uniformity, the idea that there's no specific periods of training and testing, that in fact we imagine systems that can and should learn continually from raw experience. This is a great example of that temporal uniformity, that there's no special training and testing periods that a person and a device undergo. So my objectives for this talk today, one is to not drop this microphone, which is getting heavier and heavier in my hand because I'm a chronic pacer and I can't stick with a fixed mic, that we have a shared set of terms that we can talk about after this. And two of those terms are constructivism and continual learning as the phrases I'd like to go back to, and a minimal set of concrete examples of what's technologically possible right now. And I'm going to ground this in work that we've done here at the University of Alberta largely. Such that we can actually discuss, all of us could go out to the pub and discuss clearly the similarities and differences and merits of those different pathways I just showed you for meeting the needs of users. Cool? Cool. Everyone's, oh, yeah, most people are just like, yeah, we're great with that. Keep going. Show me some robots. Okay, I'm not going to show you a robot. I'm going to show you this. I like this slide. I like going back to the slide, and like poor Adam is saying, like, I've seen the slide 300 times, just different views of it. This is the Cairo Toe. It's a prosthetic device that's over 3,000-year-old. And it was, there's a great article about that in the Lancet if you really want to go check it out, and another in the Atlantic. But this is a ancient prosthesis. It's an ancient device worn to replace a part of the body that was lost. And one of the things I think is cool about this, and if you go through the article, there's the evidence that this device was adapted and sculpted to the user more than one time over the course of its use as the person changed and their environment changed. So this is an old prosthesis. I'm going to contrast that with, if the video buffers properly, it does, with some of the robotic limbs. These are a selection of limbs we have in our Blink lab here on campus. There's commercial prosthetic robotic hands. There's a series of devices with individual actuation of digits. We've used additive manufacturing to build our own multidextrous hands, some of them that people in this room have used or played with in various ways. And this is quite a step change in terms of sensing technology, actuator technology, fabrication technology, and computing technology, especially computing technology that's customized for machine learning, from that Cairo Toe that we had 3,000 years ago. Not surprisingly, it didn't have much computing technology, although it had a little. Mechanical compute is a thing. And so with mind to that, let's just zoom in on some of the things that are present in the interactions between people and those different neurotechnologies, the snapshots I just showed you on that last slide. The first path that we often think about, and most of the time we only think about this, except for like Adam, he thinks about the other pathway I'll show you next. But for the most part, people really dominantly think about the pathway of information flowing from a person to the device that's assisting them in their life, the control pathway, a way of sampling the user's intent by way of signals from their body and mapping that to say how an artificial limb might open and close, or how the limb might move in space in response to signals from the human body. Not surprisingly, in recent years, machine intelligence has become the main broker of that relationship. It's formed this universal glue, I'd like to say, between the signals from the person and the way a device is in fact being used. So this is increasing the number of functions, or the modes and functions that someone can in fact control based on signals from their body. I mentioned the feedback pathway is this other pathway. Often this goes completely ignored. For the longest time in commercial, clinically deployed artificial limbs, the feedback pathway was someone staring at their hand while they pick something up. Maybe they hear the whir of the motors. But for the most part, the feedback pathway has for decades and decades, in fact, thousands of years, I would argue, been mechanical, sometimes auditory, and mostly not in any more deliberate way controlled and brokered by the device. And so folks, I'm just keep pointing at Adam because I'm actually going to cite some of his work, is that in fact, machine learned feedback is now becoming a thing. We are actually starting to care about this. And now we can make the same argument that in fact, adaptive machine technologies can start to broker the relationship from all the things that prosthetic arm is able to perceive to the signals that are delivered back to the human body for their own processing and decision-making. I'll also say that we are very lucky to live in a time when there are some spectacular surgical interventions that are now at the disposal of our surgeons right here in Edmonton. The surgeries like targeted motor reinnervation, first pioneered by Todd Kuiken, the rewiring of the nerves of the peripheral nervous system so that the nerves that would have gone to the amputated limb to control its motor control functions are now rerouted to other existing muscles in the body. My colleague Jacqueline Hebert and her colleagues brought sensory reinnervation here to Edmonton, the rewiring of the sensory nerves, that you actually take all those sensory nerves that would have gone to an amputated hand or arm, let's say, and rewire them to the skin of the body. And some work by other colleagues here, along with Paul Marasco from Cleveland Clinic and John Sensinger from UNB and others, looking at how kinesthesia and proprioception, the feeling of where a limb is in space and how it's moving, might also be mapped back to the human body by way of different technologies. I'd be remiss in not mentioning this as well. I think it's really exciting. This is one example of osseointegration, the direct integration of bionic limbs into the bone structure of the human body. What I'm showing you here is an example from an article by Max Ortiz-Catalan and his group, looking at how, in fact, the robotic limbs can be attached directly to shunts that are implanted within the bones of the residual limb. And what Max's group has done here, I think is really exciting, is they've in fact run wires through that shunt and connecting directly to the nerves and to the muscles, so that when you attach the robotic limb to the arm and Allen key it in place, there's also an electrical connection. So there's bidirectional flow of information to the nerves and to the muscles of that residual limb. This is pretty science fiction cool. And we actually have some great lower limb versions of this here in Edmonton already with the Glenrose Hospital and also the work that we're doing in phys med rehab and medicine. So, okay, how is that? Like, that's sort of a very cool, I hope, view into the different factors and considerations. And by showing you all that, I hope we can still agree that in these areas, prostheses can be improved through the adaptation sculpting of them to individuals, their unique bodies and needs, especially for something like osseointegration. I would hope that you would sculpt, the implant to the bone of the person that was receiving that particular surgical intervention. I'll say even more, though, that modern prosthetic technology, in my opinion, has all of the necessary preconditions to, in fact, construct or enhance many elements of those interactions that we just looked at, the control pathway, the feedback pathway, and even those surgical interventions, that the technologies now can, in fact, for themselves, construct or optimize those elements while they are being deployed with a user, not just in the clinic or not just at design time. And this brings me to one of the things that's near and dear to my research, and also I'm sure Gotham's research as well, and others in the room, I'm sure, is something that's termed continual learning. This is a branch of machine learning that embraces the idea that a machine might learn in a constant, incremental way, develop things like knowledge and behaviors in a nonstop way that exists over the divide between task boundaries, that allows knowledge and behaviors to be built upon other behaviors, and that allows a system to adapt and change over time in a continual or a nonstop way. This is continual learning. If you're interested, Kimia Kurtapal and Doina Prekup have an awesome review paper from 2020 that I would encourage you to look at. And Mark Ring, back in the 1990s, had a really great view into this that I also recommend. So this is not a new idea, but it's an idea that is now technologically pragmatic. So you might ask yourselves, maybe you do, I don't know, maybe none of you asked this question, but like, what might a prosthesis control system continually learn and use? Like, what part of those control and feedback pathways might we imagine being continually adapted over time during use? And for those who've seen talks from me before, I often like this slide where I think about the pathway of technology, especially intelligent technology in medicine, as being a pathway moving from data to the achievement of goals by way of certain decisions. And what underpins that, the through lines in this, are the representations that a system might build, the way that the information of the observer, like in Gotham's talk, all that state information that was flowing into the agent from the world, like how that is then represented in a way the system might learn based on it. The predictions or models that a system might attain or build based on the information flowing from the world. And then the policies, the action selection things, like how a robot gets to its charger, that an agent might build based on those representations and the predictions. For this talk, though, I'm really going to focus just on predictions, and especially with like Gotham's constraints in mind. I keep those heavily in your mind because they apply to what I'll say as well. Is that I'm going to focus just on the prediction bit. I think Gotham, thank you for taking the control bit. I don't have to worry about it, so we can just like leave that one as a wash because you already fully did it. So I will say though that reinforcement learning techniques are very, very well suited to continual learning of predictions or control behaviors, and are able to capture long forecasts about patterns of behavior or patterns of activity or signals of interest. And you can see this even back in the early papers from, say, Rich Sutton and in the temporal difference paper from 1988, talks about predicting temporally extended signals. So the key example I'm going to use for most of the remainder of our time together today is something that we've built in the lab over the last more than a decade. It's the methods for adaptive and autonomous switching. This is sort of like, I use this as my model mouse or my case example of continual learning deployed in prosthetic interactions. This starts back in 2011, 2012. We were working with participants who just had those targeted motor reinnervation surgeries, some of the first ones ever to be done up here in Edmonton. And we had these individuals using their, you can see in the sort of the B side of the slide I'm showing you right now, this is an individual who has nerve rewiring to have extra control sites on his residual limb such that he can begin to control a robot arm. And we had these individuals with reinnervation surgeries controlling a robot gripper to be able to pick up a ball, drop a ball, move objects around using the signals from their reinnervated nerve tissue. And during that, we showed as well that a machine learning system deployed in that stream of interaction could in fact begin to continually build and adapt predictions about aspects of that data stream, about the forces that someone might be applying on a ball, about the way that that limb was moving under the human's control, and in fact the positions and orientations of the robot limb system under the person's control. We deployed prediction learning algorithms, temporal difference learning algorithms, if that means something to some people, to be able to build up forecasts of how that person and the machine's interactions unfolded over time. We've showed not just like I showed you like 3 predictions on that last slide, but we showed it's highly scalable. We showed that we could deploy on a complex robotic system like this one, the modular prosthetic limb, tens of thousands of predictions that could be continually learned in real time about all aspects of motor control, things like the position, velocity, and loads on this robot arm, the temperatures, and all of the joints, different aspects of behavior. We have a cool paper called Prediction Surprise and Predictions of Surprise, where we even showed that the system could be surprised about unexpected deviations, like me walking up and shaking the robot's hand while I was expecting to be doing a different motion. So we showed that not just the ability of a system to make 1 or 2 predictions, but to build whole cohorts or populations of forecasts about the future during ongoing interactions, and where those predictions might even be built on other predictions. So with that in mind, I'm going to say that the reason how I tie this to the ideas of adaptive switching is that one observation we came to from that process was that, in fact, there's a very powerful gateway to enable adaptive interactions in neuroprosthetic devices. It's that we can think about mapping learned predictions to fixed outcomes. This is one step back from what Gotham showed earlier. This is not trying to have the machine learn how to control all of its own joints or motors. It's that a system can continually learn to predict the future, to understand what's going to happen next, and then create hard-coded mappings from those predictions to the behavior of this neuroprosthetic device. Predictions, in fact, for the case of adaptive switching, change a person's interface to that device. So one very common, I was talking about adaptive switching, so let me just say a little more on it. The idea of adaptive switching relies on the still convention that we see in many clinical applications, but also prosthetic limbs, of a person being faced with a technology that supports them in their daily life that has many, many modes and functions. So for now, imagine a robotic limb with an elbow and a wrist joint and wrist rotation capabilities and maybe independent fingers. But a person, because of their surgical setting or the way that they are able to interact with the system, only be able to control a limited number of those modes and functions at any given time. So in a prosthetic limb system, for instance, someone might actually just like bump their chin on their shoulder to hit a mechanical switch to change their control, the voluntary control they have between, say, the opening and closing of a hand and the bending of an elbow. So this is a very common setting, not just in limbs, but in everything from, well, I'll show you later, exoskeletons, and there's wheelchairs as well. And so what we did, this is a very straightforward thing, and I want to show this as an example of continual learning, is that we looked at how, by making predictions about what modes or functions someone wants while they're using a limb. This is a gentleman with, again, someone with upper limb amputation who's controlling an arm to just do a simple task, move back and forth in space and either open and close the hand or wave the wrist. And so what we do is just actually forecast what kind of things, what kind of joints this person is going to use in a given situation, and then just reorder the list of modes and functions based on those predictions to give him what he wants when he wants it. And you can see, I love that little bit in the video. He like tilts his head like, oh, wow. It like, he like the first thing you can see here we have him switching between modes and functions in a very visible way with his hand. And if you watched at the beginning, he was switching many times to get to the motor function he wants. And by now he switches once and he gets exactly what he wants when he wants it. So that's the idea of adaptive switching. I'm going to skip over, this is all about the predictions. I'll skip this in the interest of time. But to say that one thing that we found over a series of studies, this was largely captured in Ann Edwards' master's thesis, a really excellent master's thesis, I think, showed that through using predictions to modify a control interface in a hard-coded way like this, was able to reduce the time it was required for someone to do like ball manipulation tasks, like moving objects across a barrier, and also to substantially reduce the number of switches that a person had to, in fact, do to complete that task, reducing both the time and the load for the person. It wasn't just that, it wasn't just moving a hand and waving it on side. We've showed that this is applicable in work by Pooria Faridi and Vivian Mouchoir's lab. We've done some cool work on adaptive switching for real-time exoskeleton control, switching between the modes and functions. Pooria just offended on Valentine's Day, so this work is now fully out in the world in that way as well. Ashley Dalrymple and others in the Mouchoir lab as well looked at intraspinal microstimulation for walking, standing and walking in cats. We've looked at it for robot limb failure and anomaly detection, look at hazard prediction and other things in both VR and robotic settings, and also coordinating upper limb synergies and like looking at how you might coordinate multiple robotic joints. So it's not just adaptive switching. We've looked at continually learned predictions being able to impact a number of different control interfaces across a range of different assistive devices and technologies. We also have looked at reinforcement learning, just to be clear. Some of our earlier work, turns out it's really hard in prostheses, but we have looked at like humans delivering good, bad feedback to actually train a prosthesis controller to interpret the signals coming from their body. Literally a person just being like, yep, that was great, nope, that's not great at all, yep, that's super great. So like the reward signals, those reward signals Gotham had for the Anki vector going to its charging station. Imagine that a person's actually given those thumbs ups and thumbs down to train their limb system how to behave. So that is a very interesting, it was one of the first examples of that ever in the literature. So I will say, continual learning is a basis for all of the things I just showed you. These are all methods that are scalable in that they do not grow in terms of the compute they need or the memory they need over time. They are something that could in fact be deployed on limb systems because of those computational requirements. And that enables constructivism, which is a cornerstone of adaptation sculpting to individuals. For those who don't know about constructivism, it's most well known because of Jean Piaget and thoughts on child development, but it really is the perspective that perception, knowledge, understanding, abilities, behaviors, and skills are constructed through interaction experience. They're not hardwired on birth on any organism, but they are in fact something that is built over time and through an inherently continual learning process or an adaptive learning process. I think this is something that we see in like the examples from last talk with dogs jumping up and grabbing things. A lot of animal learning can be seen to be constructivist. There is some hardwired stuff too, to be clear. But like I have a child and there's definitely some constructivism going in my child, that's for sure. So continual learning and constructing control and feedback, in my opinion, is essential. This is sort of my soapbox part of the talk to say that it's in essence putting the person and their needs and goals front and center in how they interact with assistive technologies. It's a way for those technologies to, in fact, be tasked to optimize for what someone wants, not what some designer thinks a person needs, but of what a person actually needs. And through a process of continual adaptation, technologies do then have the capacity to be driving forward a person and their journey through their own life. I think that's really powerful. I think it's really exciting. And I think there's solid evidence, like we've built a huge body of evidence over the last decade in our lab, that this is now computationally and technologically possible with like our current prosthetic hardware, not the prosthetic hardware of the future. And then the questions we have is like, is now the right time for this? And what critical evidence do we need? And I think these are open questions. We can discuss it more perhaps later during the question session, but I do think we have excellent measurement technologies. I think we now have the ability to quantify it and in many different ways and qualitatively assess those interactions. We have protocols for this. We have all the right compute. We have the algorithms we need. In terms of critical evidence, we don't have long-term understanding of how a machine and a continually learning device co-adapt, or what the hallmarks of that long-term co-adaptation might look like. This is something we've never done as a species before, so we should really figure it out. Our smoke ferns are the closest thing we have, and they don't really cut it for the kind of studies that we need. So I think there's bodies of evidence that we do need to move forward in this area. I will say though, that this is like the bullet point of the talk, is that I showed you the control and the feedback pathway. I do think of that thing that lies between, that's both infinitely thin and also infinitely broad, as a universal glue that can connect a person and a machine. And that in fact, constructing and updating that through continual interaction is going to allow us to completely and radically transform the way we think about neuroprosthetic technologies, the way we think about how people interact with assistive devices that are tightly coupled to their bodies. We can do something that I think we've never considered before, in fact, which is going beyond code channels. For the history of rehab technologies and neurotechnologies, we have predominantly thought of it as a putting of bits upon wires, that some kind of human motor intent will be encoded upon a wire. It'll shoot through something, it'll be decoded inside the machine so that it does the person's will, or vice versa, that there's an encoding and decoding process. That it really is all about bits on wires, and we just need to make sure that those bits capture everything that the person wants. But there's another way, there's a gentle and powerful way that I think we can now avail ourselves of because of the model building and the complex capacity of our modern artificial intelligence algorithms. We can start to appeal to things like extensive inferential communication, as Tom Scott Phillips has put forward, or the joint action models of people like Natalie Sabans. Models and frameworks wherein two parties act together within the shared world and build models of that world and each other, so that a small nod or a grunt or a twitch can pass massive amounts of information because those parties share those models of their world and of each other. We can actually move towards emergent or fully constructed interfaces, as opposed to keep banging our heads against the almost impossible task of increasing the capacity of our coding channels. So I want to say this takes us to where like J.C.R. Licklider from the 1960s would have been shocked and marvel at this. Ashby from the 1950s would have said this is truly us being able to amplify the power of selection and choice, much like we amplify our physical power. Licklider's quote from his paper in 1960, I think is quite telling, is that someday soon we can imagine, I'm going to paraphrase, humans and machines being so tightly coupled that they begin to think like no human has ever thought and process information like no computational device currently known to our species. So this is where I think we are now. And I do believe that the confluence of our technologies are going to allow us to completely and utterly change the way that we interact with all of our technologies, but especially our neurotechnologies, such that we truly can become more than the sum of our parts. So with that, I'd like to thank everyone here and a lot of people who've contributed to these ideas I shared with you today, including folks like Gotham, who came earlier, and others in the audience. I'm just going to, I'll keep saying Adam's name. So anyway, thank you all very much for having me, and I'm very happy to take questions now. I hope our poor videographer, I wander as well. I hope you weren't like having to, I'm the worst for videographers. I'm so sorry.
Thank you for that message. Earlier on, we were talking about how humans how deep does that go? Is it just mentally?
It is holistic, in fact. I mean, you will see that people will, of course, start to, there's some really cool, I'll just take a tiny tangent and say, there's some really cool neuroscientific evidence that shows that people will, in fact, begin to incorporate the tools they use into what's called their peripersonal space, the space that they can reach and act upon. So think of it like the neural populations in the brain actually shrink wrapping to incorporate like a pen that I'm using to poke at something, or the microphone I'm holding, or a hockey stick, or a neuroprosthetic device. So there is a very interesting both transient and long-term process of remapping wherein people are in fact able to incorporate their devices into their sense of self. So that goes towards embodiment or tool incorporation. And there's a long history of literature that says, yes, people will on very shallow and deep levels, both temporary and long-term, incorporate these devices and adapt to those devices. So that's we do this all the time to all of our tools. I now have a smartwatch. Previously, I got a smartphone. Before that, I had a flip phone. I have changed my behavior radically, sometimes for the worse, sometimes for the better, because of these new technologies. So I think that's like, we can see that there is physical adaptation. So if someone is using a technology, even think I showed you the osseointegration example from Max or Catalan. If someone is not loading that device, the bones will not incorporate in the same way into that implant as they would if they were actually lifting heavier objects. So there's like physiological changes that happen. The nervous system, the peripheral nervous system also adapts, and the body itself adapts. People adapt their choices and how they use their body and they live their daily life, which sometimes, and that's one of the reasons why we have some of these new surgeries, because people will adapt in maladaptive ways. Like imagine you don't have the ability to rotate your wrist. How might you pick up the pen? I might have to rotate my elbow up like this and go like this. So there's compensatory movements that people build into their daily life behavior, which causes long-term strain injuries, stresses, or other chronic conditions. And so the question is you're correct in stating that in fact there are very deep ways that adaptation process from a person to a machine happens. And now if you also have a machine that's adapting, you can imagine that this gets quite recursive and quite interesting. Anton.
You said that there was some feedback. So learning goes one way when you're from that. And then you said you used to do a thumbs up, thumbs down for continual learning. How is that done now? Thumbs up, thumbs down. When the person takes their new into them out of the lab and you say it has to learn from them. If it's not thumbs up, thumbs down, what's the feedback?
So I will say that I would never want someone to be consistently delivering a thumbs up, thumbs down signal during daily life. That's insane. And we would never deploy that outside of the lab. Like this is a showing of possibility of tabula rasa learning from a blank slate based solely on and uniquely from the human preferences. So that's like a human alignment showcase. I would not deploy that. I would say that there's a gentleman sitting behind you who did an excellent thesis on learning from using reward, learning from demonstration. So using a healthy biological limb to teach a robotic limb. This is something that actually does also rely on that same good, bad signal. But in this case, now it's a demonstration signal, and that does potentially scale outside. There are other methods that we've proposed over the years for looking at human preferences or impressions of how a device is doing. Vivek Virya had a cool thesis on face valuing, extracting value functions from just the facial muscles and the way that the human face moves. And also there's been other work by other researchers looking at other cues that can be mapped to reward to allow long-term training of good, bad feedback. I find this quite complex, which is why you can see that I pivoted in terms of like a decades plus long research portfolio change, is that while we have still pursued a lot of policy learning, again, like Gotham was showing the policy learning approaches, that we've pivoted to studying in depth the process wherein learned predictions are mapped in a fixed way to control and feedback signals, because the learning is ridiculously fast, it's ridiculously adaptive, and it requires very low compute. So we've camped on that for almost 10 years now in a very concerted way, because it is something that promises to scale quite readily outside of the lab environment without too many checks and balances needing to be put in place. Yeah. Thank you. More questions? Yeah, this is, I mean, I wish I could just like summon my colleague, Dr. Jacqueline Hebert. She's amazing. And she knows this, like she's a clinician. So she knows this literature quite well. I will say that there is some effect. There is some effect like the mirror box therapy where being able to volitionally control a system will help to allow that phantom limb to either telescope and disappear or to be projected back out into the new device. That was one of the motivating factors actually for the targeted reinnervation surgeries. So when Todd Kuiken first developed this down in Chicago, like it was because of, actually in that case, it was because of neuromas, like bundles of nerves that are getting into trouble. And it's like, well, hey, if we just like cut them apart and then attach them to actual muscles and give them jobs, is some of that like limb pain going to go away? There's some phantom limb pain and neuroma pain. And the answer was yes, but then it also turned out that the person can then volitionally control those tiny groups of muscles. And that was a huge bonus. And now that's like one of the big outcomes. But that one in particular is interesting because it does, when you have that sensory and motor bidirectional connection to actual nerves, it does let the brain go back and connect to something. And so there is, I believe there's a solid body of evidence showing that it does actually have an impact on phantom limb pain. I am not in the best position to tell you like, oh yeah, this thing totally does it like 5% better or not. I haven't dug into literature too well, but I would say that there's an overriding trend, which I've seen at least presented, which that some of these, that the increase in the ability to control a device and to, again, shrink wrap your brain over it. So you feel like it's part of yourself. It has been correlated with a change in a reduction in phantom limb pain in the presence of phantom limbs in sort of complicated configurations. Thanks. That's a great question, but I'm sorry, I'm not the right person to answer it properly. Wow, more questions. Sure, please. Maybe there, then there.
We see a major obstacles of things for moving these examples in parts of the warfighters or any other sort of.
Yeah, so I think like one cool example that just says, hey, some of this stuff works in lower limb is the work I noted about from Poria Faridi in his recent master's thesis, which was saying, hey, almost the same adaptive switching that we used in upper limb prostheses could be deployed for lower limb locomotion, which is standing and turning. I will say that lower limbs, actually, I'll just pick on lower limbs for a second because they have some really nice properties that, unlike upper limbs where there's these, I might be doing all sorts of weird things. I might be like doing this while I'm giving a talk. Lower limbs have much more repetition, cyclic behavior. There's more reliability in them. And so in some cases, we don't need to apply the same level of complexity to get good efficacy in lower limbs. Like there's a lot of microprocessor controlled leg systems, which can use reasonable algorithms, machine learning or otherwise, to be able to generate gait patterns at different speeds and to be able to detect changes in stairs and things like that. So we're seeing a lot of enhancement there because the lower limb has some constraints upon what a limb might do that allows developers and designers to essentially box in some of the algorithms. Upper limb, I like it partly because it is sort of the Wild West of trying to figure out what the human's intent was in a very vast possibility space. Lower limb still complicated, don't get me wrong. It just, I think that we've seen a lot of really rapid progress in lower limb because there are some reliabilities and regularities in lower limb. But a lot of what we've talked about today totally translates over to, like, again, spinal stimulation systems or to wheelchair technologies or like any kind of human machine shared interaction or interface. There's a lot of transferability, partly because it is a very agnostic to the data streams coming in and going out. Like you could do adaptive switching on, I know Adam has used it, and like large like fighter, what was it, the airplane example you had? Like you had the a cockpit of an airplane, I think was one of your slides. You also had like a Gundam suit, I think, in one of your talks. But so like there are examples where you can imagine any kind of human interaction with a very complex system that like you could just translate the idea over without too much tweaking or fiddling with the way it is deployed. It's a similar answer to what Gotham gave for the vector Anki going from LiDAR to vision. Like the underpinning algorithms don't require much of a change. There's something about the state representation, that's sort of where the observations interface with what's agent state is, that might take a little bit of tweaking, likewise for the action outputs. But the core algorithms are in fact quite general and transferable. A similar answer to Gotham's. Last question, I think, or is it none questions?
Yeah, we have one more time for one more question.
Sorry, one more time, please. How would reflexes? Actually, this is really like, this is really quite nice when we think about reflexes. So there's sort of the, I'll actually go a little bit more into what Gotham had in his slides, which is to think about sort of the classical conditioning and the operant conditioning approach. I think that a lot of what we see here are in fact examples of what might be hard-coded responses to learned predictions. This is very much like the eye blink behavior in animals, like a rabbit's running through the brambles and there's a puff of air, it's going to predict an impact to its eye and close its eyelid. And so a lot of the basic mechanisms of things like reflexes and more advanced reflexes, the kind that I think are really cool, not just like the knee kick loop, but in fact, things like changing heart rate, muscle tone, and things like that. Those operate in the cerebellum. A lot of those are done through cerebellar processing. Like there's all those cool Purkinje cells on the surface of the cerebellum that go through the deep cerebellar nuclei and project out into things like the places that change heart rate or other decision making. The algorithms we're using here, that like the temporal difference learning algorithms, in fact, can be seen as analogs to those Purkinje cells in the cerebellum. So there's like this really natural biologically inspired link between the kinds of approaches that I was showing you today and the more advanced reflex-like behavior or anticipatory behavior that we see in a wide range of organisms. So it's actually pretty cool. So I think, yeah, like this is great for reflexes. In fact, it's one of the things like, yeah, what can it like, oh, I'm going to plan out how you're going to get to the airport or your next trip to like Milan. No. But wow, can the systems I showed you today like help like stop you from smashing into something at force, or to pull back quickly when there was like something hot that you couldn't perceive, or to prevent damage or impact to you or predict hazards? That's 100%. That time scale, that window of decision making is very much what this work is geared towards, and also really important for the kind of rehab domain that we're looking at. Yeah. So I think that's a great question. I love it. Thank you. And thank you for having me. This is wonderful. And now hopefully we can all get back on time for the program, even though I'm sure I went long. I'm sorry.